All right. Hey, everyone. Welcome to the ASEN 3728 Aircraft Dynamics bonus lecture that will give you a taste of optimal control. So, I mentioned in class that there's this other method of doing control that we didn't really get to cover in the normal lectures called optimal control. And I really think it's awesome. I think it's kind of the next step from these kind of gain tuning type things that we did during the class to kind of the next level of control. So I just wanted to give you a taste of it. Didn't get to do that in the normal lectures, so I'm going to do it now. So in the class, we basically had this control problem. So we had some system described by a state space dynamics equation, x dot equals ax plus bu, and we tried to choose a gain matrix so that if we set u equal to negative k times x, then we would have a closed loop dynamics matrix, a closed loop, which is equal to a minus bk. And we analyzed the closed loop eigenvalues of this matrix, also which are the same as the poles of the closed loop transfer function. And we tried to choose k in a smart way in order to make those eigenvalues better, having a better damping ratio, for instance, changing the natural frequency, changing the response. Now, we had three ways of doing this in class. The first one was just pole assignment. So for very simple problems, we could choose essentially eigenvalues that we wanted, or maybe a damping ratio and a natural frequency. And we could by hand calculate what the gains should be in order to accomplish that with a given control architecture. The second way that we did it was just through hand tuning of the gains. So if we couldn't calculate the gain values by hand, we might just have a simulation of the system, and we would change the gains, adjust the damping as we could see, the response or how the eigenvalues moved, and just kind of do that manually and heuristically. And then the third technique that we used is drawing or plotting the root locus. So the root locus, if the polynomial, the characteristic polynomial is too complex for you to calculate gain values by hand, you can just draw a plot of what these what the eigenvalues will be at different gain values, and that makes a root locus. So today I'm going to talk about a totally different way of approaching this, which is called optimal control. And this is a pretty powerful technique if you want to do something like land a rocket booster, like Blue Origin is doing in this picture, where you have some very important constraints, like you can't crash, you can't hit the ground, and you want to calculate precisely what the control should be to accomplish this. Then you're going to want to use techniques from optimal control. And these are the kind of techniques that these engineers actually use for this. Okay. So in order to talk about this, we need to have, I'm going to review something that you may have seen in some form or another, which is the mathematical concept of an optimization problem. So in an optimization problem, there's kind of two elements to it. There's the objective and some constraints. So the form that we use to write this, the standard form of an optimization problem, is minimize some objective function, f of x, subject to some constraints, g of x is less than or equal to 0. And then we have some variables that we get to change to change the value of the objective function. So as I said, This is the objective. These are the constraints. And the variables that we get to adjust and change are the optimization variables. Now, you can think of an optimization problem as a way to interact with a computer. So sometimes we write code to get a computer to follow the procedures that we want. Another way that we can use a computer is by specifying an optimization problem, specifying this objective, and then letting the computer solve it, because computers are very good at, in a smart way, trying a bunch of different values of x to see which one is best according to the objective function. So we as engineers, when we're doing optimization, we specify f and g, and then we let the computer find the value x star that minimizes f of x subject to the constraints. So previously, when we were doing control, we were finding the gain values more or less by hand. In optimal control, we'll let a computer find not necessarily the gain values, but the actual control values themselves. Okay, so in a simple example of an optimization problem, a very important one actually, is the following. Optimizing a quadratic function. So if we just say minimize x squared, we can adjust x. X is just a scalar here. Earlier up here, x could be a vector. And we have subject to x plus 2 is less than or equal to 0. So I can draw this function and we can just inspect it visually to see what the minimum is. So here's my function x squared. And then if I say that x plus 2 is less than or equal to 0, that means that x must be less than or equal to negative 2. So I can rewrite this as x. I can move the negative 2 over to the right-hand side. And I can kind of mark that region here if this is x equals 0 and this green line is at x equals negative 2, then this whole region over here is infeasible. And we can see that the objective, this black line here, minimizing x squared, if we're in the feasible region to the left of this green line, the point that minimizes it is right here. And that is denoted x star. X star is equal to negative 2. And we have f of x star, which I'll denote by f star. This is the value at the optimal point. And that is equal to negative 2 squared, which is equal to 4. So that's just an example of an optimization problem. It's a really simple example. We might also have more than one scalar variable. So if I say minimize a sum of squares of two different variables. So I now have a vector x, and my objective could be, for instance, minimize the first element, squared, plus the second element squared, subject to x1 minus 1 is less than or equal to 0. Then if I draw this, I now have two kind of optimization variables. I have, we'll call it x1 is in this direction, and then x2 is kind of in this direction. So these are kind of on a two-dimensional plane. And then the objective, I'll make this in red here, is like a kind of bowl in 3D space. So I don't know if, hopefully you can kind of see this bowl that I'm drawing here. I guess I can make these are like lines where f has the same value, topological lines on a topo map, basically. And so it makes this kind of bowl structure with these two optimization variables, x1 and x2. So if I draw this looking straight down from above, then it'll look like this. Okay, our objective will have these kind of lines where, for instance, where x squared equals 1 and x1 squared plus x2 squared equals 2, x1 squared plus x2 squared equals 3, etc. And then the constraint will be x1 minus 1 is less than or equal to 0. You can rewrite this as x, let me do it in green just because it was in green on the other one. X1 is less than or equal to -1, +1. So that's just saying that everything needs to be to the left of this region. So the optimum here for this 2D case is, so we can actually solve for this analytically. If you remember, probably you covered this in your calculus class. If we want to solve for the point at the bottom of this bowl, we can solve for the point where the gradient of f, which is the derivative with respect to each of these individual variables, equals 0. And if we do that, we will get x star, the optimal point, which is right here, is equal to 0, 0 in this case, just by inspection. So if I want to write out this gradient, we're gonna do this later. And this is, by the way, there's entire classes of material on optimization. You can study it from many different perspectives. There's many different algorithms for it. So this is just kind of hopefully refreshing your memory about some things from maybe Calc 3 or so. But just to write out how I calculated this, the gradient of f with respect to x is equal to del f del x1 del f del x2, and that's going to be equal to 2x1 and 2x2. So this is going to be 0 at x star equals 0, 0. Okay, so if we're in a feasible region where the constraint is not preventing us from getting to this local minimum, then that is the optimal point right there. There's a whole theory involving things called Lagrange multipliers that tell you how to rigorously solve these constrained optimization problems. We won't really need that today because we'll be focusing on a problem where the only constraints are dynamics, so there's no constraints on what you can hit. So this is kind of hopefully jogging your memory about optimization. We can apply this to control via the techniques known as optimal control. And the general form of an optimal control problem is minimize. Well, this is one way. There's multiple ways to formulate optimal control problems, but we usually want to minimize, and our control variables are actually trajectories. So this is a function x as a function of time and u as a function of time, and we get to try to minimize those of j of x of t, u of t. This is our this j is our control objective function, and then the constraints that we use are the dynamics constraint, which is subject to x dot of t equals some dynamics function f of x t and u t. So if we're using a linear model of the aircraft, this f would be ax plus bu. We could also use potentially the nonlinear model of the aircraft. And then we often have, in general optimal control, we have some constraints on the state. So we might have, we might say that x min always has to be less than or equal to the state at any time t, which is also less than some x max here. And then we might also have some constraints on the controls, u min less than or equal to u of t, which is less than or equal to u max. So if we're talking about landing a rocket, I'll just, copy this down here for inspiration because it's a pretty cool problem. Then our state, we might make our objective to be close to the landing zone. So we might have some state that is being on the ground, which is x target. And so therefore we might have j of the objective function is j of xt ut equals the distance, the integral over time of the distance between xt, the state at the current time, minus the x target. And these double lines are just a norm, so it could be like the 2 norm for instance. So this will make you'll want to get close to the target. We might have additional constraints. Our x min and x max constraints might mean that we have a constraint that's like if theta is the angle between directly up and the angle of the vehicle, we might have some constraint on that we don't want to tilt too far over. So we might have a constraint like theta min is less than or equal to theta at time t, which is less than or equal to theta max. Something like that. We also might have constraints on the fuel. There might be actuator constraints, etc. So these constraints are nice because they can keep you from getting in states where you can't recover from, or from hitting things like the launch pad or hitting the ground too fast. So this is why optimal control is useful, because it allows us to reason about these constraints as well as just kind of a linear gain value. Okay, so dealing with this full problem is very difficult, and there are entire graduate level courses on this that you should take eventually. Today, we're just going to focus on one simple problem, which is essentially the connection between linear control and optimal control. So this problem is called the LQR problem, or linear quadratic regulator. So this is a very special optimal control problem, and we'll see why in a second. Special optimal control problem, and like I said, it's called LQR, which is linear quadratic regulator, and it is the link between linear controls and optimal controls. So the cost function for it's called linear quadratic regulator because the dynamics are linear, and the cost function is quadratic. So let's look at what the cost function is going to be. So this is going to be j. We're trying to minimize this, and just like above, as we're minimizing this, we want to encode in this cost function the goal. And so the goal for LQR is to bring the state to 0. Now this is you can set like a target state that's different than 0 and still use this technique, but we're going to formulate it where our goal is to always get the state to be 0. So we've got j of x of t, u of t, and this is going to be equal to a quadratic function of the state. So let's say that the state is made up of x1 of t and x2 of t, and then we have some other state variables. So if I want to minimize the distance from a 0 state, which for instance, if you're an aircraft flying along and you're using your linearized dynamics, that's drawing your perturbation state from the trim state to 0. I don't want to just minimize x1 plus x2, for instance. This is not a good cost function because that would bring those variables down to negative infinity. So instead, I want to minimize x1 squared, and x2 squared. In this LQR problem, in order to get the solution form that we want, we can't have any constraints on the states or controls. So we can't have x min is less than x is less than x max, or u min is less than u, or is less than u max. So if we just used this objective function, what would be the problem? If you're watching this on video, you can stop for a second and think about that. What would the optimization solution look like for that? The problem is that will cause the controls to go to infinite values to get x1 to 0 and x2 to 0. So we also have to penalize the control inputs. So we want to minimize, in addition to the x values, you have u1 of t squared, and then plus u2 squared of t plus, all the other controls that you might have. You'll see why I'm leaving these spaces here in a second. We're driving the states to 0. We're also trying to drive the controls to 0. But these are rarely actually, we rarely care about all of the states the same amount and all of the controls the same amount. And also the units, for instance, matter. So it may be a very bad problem to have a 30-degree yaw side slip angle, but not a very bad problem to have a 30-degree aileron deflection, for instance. So we need to, because we care about these states differently, we need to actually add some weights to them. So I'm going to add some weights, Q1, Q2, and then R1. So the R's are going to be the weights on the rewards, and this are on the controls. And this allows us to decide which things we want to drive to 0 most importantly. So if we want to drive the pitch angle to 0, theta 0, then we're going to have a high weight on the theta weights. These are not the same Qs that I talked about in modal analysis. These are completely different. Okay, so if I just use this objective function, we have another problem, which is that this is only evaluated at one instant of time. So this is only at 1t. What we really want to do is drive the integral of these state deviations from 0 over t equals 0 to infinity to 0. So this is a way to represent the LQR cost function. This is not the most general version of LQR, but this is good enough for today. So one way to rewrite this with these x1s instead of this sum of weights is to put it in a matrix form. So this is the integral from 0 to infinity of the vector x of t transpose a matrix. This is going to be a diagonal matrix for this cost function. X transpose q times x of t plus u transpose r u. And in this case, Q is a diagonal matrix with these Q weights, the weights for the different states. So Q1, Q2, Q3, etc. For all of the states that you have, all the way down to Qn. And then R is a diagonal matrix of R1 down to Rm, depending on how many control variables and state variables that we have. Now, LQR in general will work for any positive definite Q and R, which means that you can have off-diagonal elements. But for today, we're just going to deal with diagonal Qs and Rs. So these are going to, if you had off-diagonal elements, they would penalize combinations of different states and controls, but with the on-diagonal elements, they just penalize the different control variables. So that allows us, with this objective function, it allows us to formulate this optimization problem based on this quadratic objective. So we have minimize j of x t ut, and then our only constraint for LQR is, and we're minimizing over these trajectories, the entire trajectory of x of t and u of t, subject to our only constraint, which is the dynamics constraint, x dot of t equals our dynamics matrix A x of t and our control matrix B times u of t. Okay, so let's talk about a more concrete example from aircraft dynamics. So this example is the longitudinal dynamics of an aircraft. So if you remember the longitudinal dynamic state, perturbation state is x equals delta u, delta w, delta q, and delta theta. So to interpret this, our Q matrix, our Q cost weight matrix, would just be a 4x4 matrix because we're going to multiply it in this objective function as, this is the thing to remember, by this four-dimensional vector here. So Q is going to be a 4x4 matrix, and it's going to be a weight penalizing QU, a QU weight penalizing U, a QW weight penalizing W, a QQ penalizing Q, and then a Q theta. And then we're going to have zeros in all the off-diagonal elements. So this will result in, if I multiply x transpose qx, this will result in qu delta u squared plus qw delta w squared, and then plus qq delta q squared plus q theta delta theta squared. So by changing qu, qw, qq, and q theta, I can prioritize what I want to minimize. And then the R matrix, I guess we could call this like the control penalty matrix, would have an entry for delta E, the elevator, and delta T, the throttle. And so that would mean that U transpose RU would be equal to R delta E, times delta E squared plus R delta T times delta T squared. Okay, so what does this mean? This allows these Q and R matrices allow us to choose which variables we want to drive to zero the most, or either which state variables we want to drive to zero the quickest, or which control variables we want to limit the most. So larger values of Q mean that when we do this minimization problem with this objective function, larger Q leads to smaller state perturbations, and larger R, and these are relative terms because we can't have our cake and eat it too. We can't both have small controls and small state values. Larger R will lead to smaller control inputs. So let's say that I want to control theta, the pitch angle, or delta theta, the deviation from the trim pitch angle. So if I want to control delta theta, I want to penalize delta theta squared. So I've got this QQ times delta Q squared plus Q theta times delta theta squared. And if I want to control delta theta, then what is my matrix Q going to be? So if you're watching this online, I'd encourage you to take a second and try to figure this out on your own. Okay, so if I want to penalize Q theta, I'm going to have zeros. If I only care about controlling delta theta and don't care about any of the other state variables, I'm going to have zeros for every element, but this 1 in the bottom right corner, and then zeros everywhere else here. So that only penalizes delta theta. I also need to have some non-zero elements in R, because again, if R was 0, then we would just apply extreme elevator, unrealistic throttle to get to 0 delta theta. So a good way to start is just one identity matrix for the controls. So now, just to think about this a little more, let's actually first divide this cost function into 2 elements so that we can talk about it a little easier. Let's say this first one is j of just the state. So this is j of x of t. And this second element is, we'll call this j of u of t. So now to think about what this LQR controller is going to do, I'm going to draw 3 examples and ask you which one is the optimizer going to think is the best. So we've got 3 different trajectories. We'll say A, B, and C. And these 3 different trajectories are just trajectories for delta theta for now. So this is delta theta. And this is time. And these are 3 different cases. So in case 1, delta theta stays constant. That's the trajectory of delta theta. Case 2, it kind of oscillates a little bit. It's got decaying oscillations. And then in case 3, it has some very fast exponential decay. So my question for you is, and again, if you're watching this on the video, which all of you are, you just take a second and answer this question. So among A, B, and C, which trajectory corresponds to the smallest j of x? So which has the smallest state component of the objective value? Okay, so take a guess at that. So if we use this Q up here, let's call this Q sub theta and R sub theta. Then j of xt is just equal to the integral from 0 to infinity of x of t q theta x of t, this one is transposed dt, which is, since we only have one entry in q theta at the bottom right, this is just going to be the last entry in x of t. So this is going to be equal to the integral from 0 to infinity of 1. Q theta is little q theta is 1 times delta theta of t squared dt. So you can think of the objective function as being kind of an integral, the area under the curve of the displacement delta theta squared. So it's not exactly equal to the area under the curve. It's like the squared delta theta squared multiplied by dt and the integral of that. So you can think of this as, like I said, not quite the area under the curve, but we can look at the areas under the curve to kind of guess at what they might be, right? So A has this long sustained constant offset. So it's going to have a very large squared area under the curve. Whereas B, the area is definitely smaller, but still significant. And in C, it's definitely the smallest. So the answer to my question, which one is going to be considered the best according to this objective function, when the optimizer is considering different possibilities, which one is going to have the minimum j? The answer is C has the smallest j of x of t. Okay, so we didn't talk, this isn't a complete description of what would be the best trajectory because we didn't talk at all about the control values, but this just gives you an idea of what the optimizer is doing. So by choosing, if we want the area under the curve for different variables to go down, then we can choose different values of this q theta and r theta. So we've kind of flipped the problem on its head. Instead of choosing gain values, we now are choosing these q's and r's. It's not like a free lunch. It's not like we can say, oh, this is the optimal way to control this vehicle. It's just changing the responsibility of the engineer from choosing the gain value k, to choosing these objective weights in q and r. So we've got this optimization problem right here with this objective function. How do we solve it? So we'll jump into the mathematical details in a second, but the short answer is that MATLAB or any programming language will actually have a built-in, any numerical programming language that people use for controls will have a built-in function to solve this optimization problem. So in MATLAB, this is unsurprisingly called the LQR function. So it's an LQR problem, linear quadratic regulator, and we can call the LQR function and feed in the things that we need to define the problem. So if we look at this problem here, in order to define it, we need an A matrix, a B matrix, a Q matrix, and an R matrix. And indeed, those are the arguments to this MATLAB LQR function. Now, I said that we were optimizing over trajectories of states and controls. The remarkable thing and the most important thing that makes LQR useful is that it has a very special form of optimal control inputs. And that is that the controls are equal to a negative gain value times x. So just like in our linear controls, we have the controls are equal to negative a k gain matrix times the state vector x. And this is very specific to LQR. So the solution to LQR is this linear gain matrix k, and that's what MATLAB will give you. Now this, it seems probably when you're watching this the first time, it'll seem pretty normal to you, like, oh, that's what controls is, u equals negative kx. This is not true if anything is different about the problem formulation. So if we don't have this quadratic form for the objective function, if we have constraints like this that are in addition to the dynamics constraints, any of those will make this not have a linear optimal control solution. So if we were actually landing this vehicle and we had some constraints on what theta could be, then we would not have a linear feedback optimal control, because when you're getting real close to that that constraint, you want to apply a lot more control than when you're only a little ways away from the theta equals 0. So it's not going to be, if we have constraints, it's not going to be a linear optimal solution. But for LQR, it is linear and optimal, or linear to be optimal. So let's look at this. I've got MATLAB fired up for y'all. So we will apply this to the kinds of control problems that we saw in class. So I'm going to fire up MATLAB. I will get my classic Boeing 747 state space model, and I'll look at the eigenvectors, the open loop eigenvectors of the longitudinal dynamics matrix. I have the phugoid eigenvectors, the short period eigenvectors, short period eigenvalues, phugoid eigenvalues here. And then I can calculate, just for experimentation's sake, the short period, an initial state that will excite the short period mode, the real part of the short period eigenvalues, and a state that will excite the phugoid mode, the real part of the phugoid eigenvalues. And for now, I'm going to mix those together. I'm just going to say x0 equals 1/2 of each of them. So this should excite both modes. So we can test this. We can, do our open loop linear simulation, and we see indeed that we start out with a short period oscillation right here in theta, for instance, this little short period oscillation, and then a phugoid oscillation that has a longer period. And then we can also plot the eigenvalues. This is everything as on the left half plane here. Got the phugoid eigenvalues and the short period eigenvalues, just like we've seen over and over again in class. Now we're going to do some magic. So we're going to use LQR to, in one line of code, calculate the gains to control these. So first, we're going to get rid of the short period mode. So there is probably a Q that I could calculate to exactly get rid of the short period mode, but approximately the short period mode involves very large values of the pitch rate Q compared to theta. So a good approximation, if I just want to get rid of that short period mode, or actually, no, sorry. The short period involves lots of oscillations in alpha, the angle of attack, which is proportional to W, the Z component of the air relative velocity. So if I get rid of this, if I get rid of delta W, then I can get rid of the short period mode without affecting the phugoid mode too much. And that's just because of, the short period mode is an oscillation. Essentially, we get this guy out. You can see him one last time. The short period mode is basically an oscillation in the angle of attack alpha. So if I want to get rid of the short period mode, I can just penalize alpha, or delta W, in this Q matrix, and then I can choose how much I want to penalize the controls to slow it down. Then I calculate this, I run this LQR command, put in the longitudinal A matrix, the longitudinal B matrix, this Q, SP, and then this R. These are the two penalty values. Run this one function, and I get a gain matrix K that will get rid of the short period mode. And you'll see that this is extremely effective. So if I start us out at this x0 state that includes both short period and the fugoid mode, I can see that it basically totally got rid of the short period mode, and it only has these fugoid oscillations. Now, this is probably unrealistic because the control values are probably pretty high. You can see that it is, quickly going from delta W of 0.4 down to 0, etc. But you can see that it really isolates that fugoid mode with very little work, just calling this one function. We can also take a look at what the closed loop eigenvalues look like for that. So if I plug in this k that we calculated with LQR and do a minus bk, I get closed loop a, get these eigenvalues. And you can see that the short period ones, the fugoid ones, remain basically unchanged. I've plotted them here. The short period ones get moved way, way out to the left here at negative 12. So they're very fast. That mode is now, very fast and goes to 0 very fast. Okay, so what if we want to get rid of the fugoid mode now? So what's the most important? So the fugoid mode, again, just to show it one more time, is a exchange of potential energy and kinetic energy. So this involves large oscillations in the forward velocity delta U. So I can just change my Q matrix, my state penalty matrix, to have a 1 in the delta U position. Call this one line LQR with now Q fugoid instead of Q short period. That gives me a different gain matrix, and you can go back and compare these to maybe gain matrices that we calculated in class to see if they're similar or not. And you can see that, boom, that gets rid of the fugoid oscillations, and you're left with only the short period oscillations. We can look at the eigenvalues, and we see that of the closed loop matrix for this, and we can see that really it's gotten rid of that fugoid oscillation. It has one real mode that's pretty close to the origin, and then it's also got these leftover short period oscillations, and then it's got this fast mode off to the real mode off to the left here. We can change kind of the aggressiveness by we can control both modes and reduce the control inputs by increasing R, and then also having penalties on all of the states. So these are diagonal matrices, and that gives us a K matrix that will control both modes pretty effectively. It, as you can see, it increases the damping ratio of the short period mode. There's short period mode right here is a little bit off to the left outside of this graph, and then it's got these two real modes right here. But you can see that it quickly drives all of the states. Well, relatively quickly drives all of the states to 0. There's this little theta that takes a long time to actually get rid of, but overall that corresponds to this mode right here. But overall, it does a very good job of controlling these both of the modes. Okay, so here's the real kicker with LQR. This is why it's effective. This is why I love it. So during the last part of class, we spent it was basically 2 class periods designing the roll controller. And you can see that here. Let's look back at our notes for this. Yeah, so we'll look back at our trusty notes. We'll go all the way to the end. So we did this entire exercise. Starts here designing our roll controller, and we had these loops, that had a yaw damper that fed back on R and changed the rudder, and then a aileron control law that fed back on the roll angle and the roll rate P. We designed the yaw damper. We did all these calculations by hand. We designed the roll controller, and then we eventually got this pretty good step response right here. But this was a lot of work to design this controller. This whole process can be done if we want to design a roll controller in these 3 lines of code. So we choose our Q penalties to be, we care most about phi, the roll angle, but we also care about R, P, and V not being too large. And then we have the control penalty R as well. And then we just call LQR on those, and we get our gain matrix K roll. And then we can create the closed loop controller, and in those 3 lines of code, we get this nice controller that drives our roll angle to 0, and dampens out the Dutch roll mode, and does great. So that was 3 lines for 2 lectures of doing this by hand. So that's why LQR is so effective, because it simplifies the task of the engineer a lot. There are caveats, reasons that you can't use LQR in all problems, which I won't get too deep into. One of the big ones is that you have to, in order to implement this control law U equals negative KX, you have to be able to measure all of the elements of the state, which is not always easy to do. There are ways to estimate those as you go, but that's one of the limitations. Okay, so that's what it looks like to actually use LQR. And if you wanted to, you could stop there and use this tool. As long as you understand what the objective function means, you can use LQR to calculate a gain matrix, and that's great. The rest of this lecture, I'm going to talk about why LQR results in this this linear optimal control, that the control input that is optimal is just a linear function, negative k, times the state. If you go to grad school, you'll realize how remarkable that is. Probably seems normal now, but it is really cool. Okay, so why do we get this solution? So our optimization problem, our objective function at least, is minimize jx of t u of t. And by the way, this math is going to be, I'm going to actually skip over some details to make it a little easier to understand. But still, this math is going to be advanced for where you're at as a junior in an aerospace engineering program. But I think even if you don't understand every single step of it, you can still get a lot out of this. So we're minimizing by choosing x of t and u of t, this objective, subject to the dynamics. So we've got x dot of t equals a x of t plus b u of t. Okay, now for the rest of this lecture, I'm going to do something that I tried not to do in class that might be confusing, which is to get rid of my normal notation with the arrows over vectors and also the function of t. So I'm going to, for shorthand, I'm going to write this objective as just x transpose q of x plus u transpose r of u times dt. Now, You're going to have to use context clues to know when I'm talking about just a scalar variable x or u and when I'm talking about the vector, but I think you can follow it. So in order to minimize this j function, we're going to introduce a quantity called the value function. And we're going to denote the optimal value function, v star of x of tau, to be the objective value that we will obtain by following the optimal control law. We don't know what the optimal control law is yet, but we're just going to define this quantity of some x at time tau to be the minimum over u. So now we're only optimizing over u of the integral from tau to infinity over x transpose qx plus u transpose ru dt. So this is going from some time tau all the way forward to the future. How does this relate to j? So the optimal objective value for the entire problem of optimizing this trajectory is j star. Remember, I defined the objective starred up here to be just the value that the objective function takes at the optimal optimization variables. So j star is going to be this value function at x at the state at time 0. So that's the relationship between them. V star is a function that you can define of the state at any time during the trajectory, whereas j star is the objective value of the original optimization problem, which involves integrating over this entire time over the entire trajectory. So v star is going to be a tool that we use to break this big optimization problem up into some smaller optimizations. So if I just take this definition here, v star of x tau, and yeah, that should be good, equals the min over u. And I'm going to divide this up into two sections. The first one is going to be just an integral over a very small amount of time. So it's going to be the integral of from tau to tau plus delta tau, where delta tau is a very small amount of time, times x transpose q of x plus u transpose r of u dt, and then plus all of the rest of time. So I'm basically dividing this up into two sections. One is before tau plus delta tau, and one is after tau plus delta tau, all the way out to infinity. And this technique of dividing this into an immediate reward and a future reward is one form of a technique called dynamic programming. So dynamic programming is breaking a large optimization problem into a bunch of small optimization problems. So we've got the immediate reward that we get just in an infinitesimally small amount of time. And then we also have the future reward that we'll get in the future. So if we're just trying to optimize the immediate reward, we can't affect x that much in a small amount of time. So the solution to this immediate reward, if we were only considering that, would just be to set u equal to 0, because that's u is the only thing that we can control. But we also want to set ourselves up for getting a smaller objective value for this future component. So I'm going to expand these out, and I'm just going to approximate this immediate reward by, since our state can't change too much in a small amount of time, this first um, reward, or this first immediate section, can be just approximated by x at time tau transposed q x at time tau plus u at time tau transpose r u at time tau. So again, and then all of this multiplied by delta tau. So we're just saying that instead of taking an integral over that, it's a constant multiplied by delta tau. And then the future, we'll notice that according to this equation of v star, this is just equal to v star, the value function, at this delta tau into the future. So this is the function at tau plus delta tau. Okay, so this is rewriting the line above in a way that might be a little bit easier to optimize. Now, the next thing that we're going to do is approximate this v star at x tau plus delta tau with a kind of a linear approximation. So we're going to say that this term right here is equal to v star at x tau plus a term that represents how v star will change as we travel from tau to tau plus delta tau. So this is going to be equal to how x changes. So that's going to be x dot. And we're going to dot that with the gradient of v star with respect to x evaluated at x tau times delta tau. So this is just essentially, this is, I'm not really explaining this in too much detail, but essentially this is saying that we'll have our value function at tau plus delta tau is going to be the value function at tau plus some distance x dot tau that we move multiplied by the gradient of the value function and then multiplied by delta tau there. So this is going to be an estimate of what our tau is going to be in the future. And we're still minimizing this over u, and then I'm not going to copy this first term down, but you can see how it comes in here. Now, we note that we're minimizing by changing u, so we can't actually change v star of x tau at all because u doesn't change v star of x tau. And on the left here, we also, so we can move this v star of x tau outside of this minimization, and it actually cancels here with this quantity on the left. So these two terms cancel, and we're left with this equation right here. This is going to be 0 equals min x transpose q x tau plus u tau transpose r u tau multiplied by delta tau plus x dot t. And actually, x dot, we know we can make this substitution. X dot is equal to just ax plus bu. So we substitute our dynamics in there. And then we have ax plus bu dotted with, or taken the transpose of, with v star And actually, I'm going to move this delta t outside of this. We can move the delta t outside of that minimization problem, and we're left with just this. And so we can get rid of this delta tau because we know that in order for this to be 0, this quantity in the minimization here has to be 0. So we'll just get rid of that. And we have this 0 equals this minimization problem. Now this equation is very special. It's called the Hamilton-Jacobi-Bellman equation. It's a fundamental equation. Well, this is the form of it for an LQR problem. But there's a more general form that is very fundamental to optimal control. So you'll see that pop up if you get into your more deeply into optimal control. And this defines what our U has to be in order to take optimal actions that both take into account the immediate reward from taking that U, and then also take into account how that U, that control input, is going to change the state to change the value at the future time. So this value function summarizes all of the future penalties that we're going to accrue in future time, and that allows us to have this Hamilton-Jacobi-Bellman equation that takes both the immediate and future rewards into account. So we've got HJB right here. Okay, so we're almost done. How do we solve this equation? So the first thing that we're going to do is make an assumption. So we are going to assume that V star of x is equal to a quadratic function x transpose sx. So this looks sort of like x transpose qx. We're going to say that this s summarizes all of the future penalties that we're going to accrue. So if we make this assumption, then the gradient of V star is equal to 2sx, which is convenient. And if we substitute this back into the Hamilton-Jacobi-Bellman equation, we're going to have 0 equals min of x transpose q of x plus u transpose r u plus ax plus bu dotted with this 2sx here. Okay, so now we need to solve this equation, and this will be minimized when the gradient of this, if we call this f, then minimized when the gradient of f is equal to 0. So the gradient here, the gradient of f is equal to 2. This is the gradient with respect to u, so this x transpose q, x term doesn't appear in here. So we've got 2 ru plus b transpose 2sx, and this is equal to 0. And when we solve this, we can just solve for u now, and this is going to be the u that minimizes it. We get that u equals negative r inverse b transpose s x. Okay, so we're done. This is the form of the optimal policy. R inverse b transpose s is equal to our gain matrix K. So we have now our form here, u equals negative K times X. This K is R inverse B transpose S. Now you'll see that S, we know R and B from the definition of the problem. The question is, how do we calculate S? So if we substitute this control law back into the Hamilton-Jacobi-Bellman equation above, we have 0 equals X transpose Q X plus negative k x transpose r times negative k x plus ax plus bu, b times not u, we've substituted back in negative kx. So negative kx here. Take the transpose of this and multiply it by 2s of x. So you can rearrange by substituting this k back in for all the k's here, and that will give us, that will actually make this quadratic. Every one of these terms will be of the form x transpose times a matrix times x. So we'll get 0 equals x transpose times this big matrix, which you can rearrange to be q plus a transpose s plus s a minus s b r inverse bs times x. And in order for that to be true for all values of x, this in here is going to need to be a matrix of all zeros. This is going to be 0 equals q plus a transpose s plus sa minus sb r inverse bs. And this is called the algebraic Riccati equation, and that allows us to solve for s. Now you'll see you can't just rearrange it and get a value for s because we've got this kind of s squared term. So you can think of this kind of as like a quadratic matrix equation a little bit. But there are ways to solve this numerically, and that's what MATLAB does within its LQR function. So that is LQR. That's how we solve it. We can take this optimization problem up here, and we can solve for a gain k so that if we take the control u equals negative kx, we will be optimizing that objective function, which I think, as you can see, is pretty awesome. So I will say, the last thing I'll say is this is how I solved P4. So if you remember homework 4 where you're trying to reach that goal in the presence of wind, you can go look at it real quick. So my solution, I won't show all of it just in case I use this homework again. But basically, I chose a new trim point. So I got a trim point where I was going as fast as possible. And then I estimated the longitudinal and lateral linear dynamics. I picked a longitudinal Q matrix, a longitudinal R matrix, a lateral Q matrix, lateral R matrix, used LQR to get gain values. And then I found a heading to go to that took into account the wind to get to the goal. So if we look at this, this time it didn't work actually. Because there's a lot of turbulence, it sometimes doesn't work. Let's see if we can get one that does. It's not super reliable. You could change it to be more reliable. Okay, so this time I got it. So the goal was to go to 200, 200 with a bunch of wind that kind of, I think, goes in the eastward direction. No. Yeah, yes. Which is down in this plot. And so I calculated a phi target, which is denoted by these blues. And then I had my LQR controller, the true phi is denoted by these red things. And then my LQR controller tried to follow that, oh, sorry, not phi, psi, the heading angle, a psi target. And then my LQR controller tried to follow that, and you can see it actually, even after it hits it, it tries to come back around and fly this way. So LQR is a very robust and easy way to calculate those controls. It only took a few lines. But anyway, I got another meeting coming up, so I'll have to cut it off there. Thanks for being in the class. It was a pleasure to have you in the class. I hope that this optimal control lecture kind of gives you some inspiration to go learn more, because this is just, like I said, a very small taste of what it can do. There's a lot of classes that you can take as a graduate student to learn more about this. One that's really good is convex optimization, which is in, I think it's either the CS or EE department, so go take that. I offer, if you've made it this far, you may be interested in my graduate class, which is called Decision Making Under Uncertainty, where we take some of these similar concepts and we apply it to cases where there's actually uncertainty about what the state is. But it's really fun. I'd encourage you, if you're up for a challenge, to take that next spring. And I guess that's it. So have a good summer, and I will see you around next year.